Welcome everyone. This is Jim Corkins, and we are continuing on with our with momentum. Now we're in 6.1, and we're going to cover conservation of momentum and collisions in one dimension. As always, if you haven't started the reading, please do so. Those readings are indicated in your Canvas course. Okay, so what is conservation of momentum? Basically, conservation of momentum is when that impulse, that force times delta t, is equal to zero, or rather the sum of the impulse is equal to zero. So during a collision, when there are one or more objects colliding, impulse is typically conserved, okay? Meaning that the impulse is zero, so that the momentum is equal to the final momentum. So the conservation of momentum holds when the impulse is equal to zero. Now, that doesn't necessarily mean that the kinetic energy is conserved, or that energy is conserved where the initial energy is equal to the final energy. But that does mean that what that does mean is that if impulse is conserved, then energy will be conserved. As long as you don't have an outside force messing with the collision, then those two things will be conserved. Okay? So we're going to be studying multiple objects, in our case just two objects colliding together, and they're going to bounce off each other or they'll stick together. Now, when I mean that the impulse is conserved with an elastic or bouncy collision, what I'm saying is that when an object bounces, and we'll do this here, this object right here has a momentum that is to the right. So it's got a mass times a positive velocity. So we're summing up the momentums. And so this is object 1, and this is object 1's initial velocity. Object 2's initial velocity is going to be to the left. And we are going to have to go crazy with the subscripts when we're doing this. Now, as you could see, during the collision, object 1 is pushing to the right on object 2. So the force of object 1 on object 2 is to the right. So that's going to be a positive force. I should probably erase this and give myself some room. So that object 1 is pushing on object 2 to the right over a period of time. So this is the impulse of object 1 on object 2. Now, object 2 is going to push object 1 to the left during that collision, and that should be a T. So object 2 is going to push object 1 to the left. So this is the total impulse right here. And that is going to be equal to, after the collision, they're saying that object 1 is moving to the left, and then object 2 is moving to the right. But this part is interesting because since these two objects are colliding, and since forces are always equal and opposite, and since that collision is the same for both objects, these two things are equal to each other. So when you add them up, the total impulse is equal to 0. So essentially, what you're left with is the initial momentum is just equal to the final momentum. So that's what they mean by conservation of momentum, is that since forces are always equal and opposite, that is Newton's third law, and since the time of the impact is the same for both objects, well, that positive impulse, which is the same as this negative impulse, well, add those two things up and that's equal to 0. Okay? And so that's the basis for this. Okay? Now that's not to say there isn't an impulse. There absolutely is an impulse going on. And when impulse is not equal to 0, that means there might be an explosion in the center. So, well, hold on. I should be careful about what I say. I'm just going to say for right now, in our class, we are going to be using that this sum of momentum for both objects for right now is going to be equal to 0. Later on, we're going to explore when it may not be equal to 0. Okay? All right. Now, let's look up at the procedure. So we're about to do multiple objects colliding with each other, and in this first case they're going to be bouncy collisions. There are also inelastic collisions where they stick together, and there's explosions where they start off together and then they blow apart. But the procedure is the same. What we're going to do is we're going to read the problem and we're going to write out a pictorial description. We're going to translate that to momentum, initial momentum. We're going to sum all the initial momentums and set them equal to the final momentums. And then we may also, we're also going to have energy, okay? So we're going to have energy, initial energy that we're going to have to sum up for all objects, and the final energy that we're going to have to sum up for all objects, okay? So that is going to be our basic procedure. Okay. Now I've expanded the useful equations, and this is all of the useful equations for this momentum and energy part of our course, which is going to be a part of exam 3. Okay, so these are all the equations that you have to know. You do have to still know how to do force diagrams, and you have to still know the motion equations, the 4 motion equations that we worked with. However, these are going to be the core of these equations, okay? This is going to be the core of what you're going to have to know for exam 3. Okay, well, let's get started on a problem. Here we have a problem, and it's one of the typical type of problems that you'll have in your homework, and it's typically written. However, how we're going to approach it is going to be a little bit different and more involved. Okay? So in these problems, as you're reading it, you should try to picture what is happening, and we're even going to write a little bit of a diagram down here. But as you're reading the problem, also write down the variables. Okay, so a block of mass m, so that's a mass, and I always subscript things with the actual mass that is related to it in these problems. So a block of mass m equals 2 kilograms. On a frictionless surface with a speed of 9 meters per second. So this, if they don't give you a direction, give it a direction, and we're going to say this guy is moving to the right. So this is the initial velocity of the 2 kilogram block moving to the right at 9 meters per second. It's going to make an elastic, bouncy collision with a block of mass 10 kilograms. So mass sub 10, and I'm going to call this 10 kilograms. And it's initially moving to the left at 3 meters per second. So negative 3 meters per second. After the collision, the 10 kilogram block is moving with a velocity of positive 1 meters per second. So it's moving to the right at 1 meters per second. They tell us that the collision lasts 0.01 seconds. so 1/100th of a second, so, which is realistic. I didn't actually measure this. I just kind of guessed, and I think all of your tutorials, I just kind of give you a number. That's somewhat realistic just because I have to solve some of the other problems that I'm going to ask you to do. Okay, well, we have to first figure out what the final velocity of the 2 kilogram block after the collision, and we need to figure out how much energy is lost in the collision. So what work is done? And then we have to fill out this velocity versus time graph and this energy versus time graph, and that's the reason why I gave you that time. All right, so there's a lot of ways you could approach this, and you could write out the initial momentum, and that would be the sum of all the initial momentums. So for example, m2 v2I, or rather vi2 as I have it written here, plus the initial momentum of the 10 kilogram block. Since impulse is not present, don't even acknowledge it. M2 V2F, V final 2, is the momentum after the collision for the 2 kilogram block, plus the momentum after the collision for the 10 kilogram block. So there's that. Okay. Well, let's go. What I suggest is, instead of writing this out, or in addition to, do this. Write a little block and put the mass on the inside and give it a little velocity vector, in this case positive 9 meters per second. Okay? And then the 10 kilogram block, do the same thing and put its velocity vector here. If it was moving to the right, you'd put a rightward vector, but the initial velocity of the 10 kilogram block is to the left. Now, after the collision, we don't know the velocity of the 2 kilogram block. That is what we need to find, V2 final, V final 2. But we do know the final velocity of the 10 kilogram block, which is going to be to the right at positive 1 meter per second. So doing this kind of helps you translate the paragraph or the description into something visual, which is always helpful. And these two things, this symbolic or variable form, is the same thing as this. All right. I don't know about you, but this is easier for me to see. It's easier for me to interpret. Okay. Well, from here, we're just going to go ahead and calculate the momentums. So this is going to be positive 18 kilogram meters per second. And as you can see, this is going to be negative 30 kilogram meters per second. This momentum is going to be 2 kilograms times V final 2. And this momentum is going to be 10 kilograms meters per second. Okay. So what we'll have on this side is negative 12 kilogram meters per second equals 2 kilograms V final 2 plus 10 kilograms meters per second. We're going to subtract this 10 onto the other side, and when we do that, we're going to end up with a negative 22 kilogram meters per second, which is going to be equal to 2 kilograms V final 2. Dividing that 2 kilograms onto the other side, what we're going to get is negative 11 meters per second. So that is the final velocity of the 2 kilogram block. And that's really how easy it is. It doesn't get much easier than that, right? Well, actually it does when we get to inelastic collision. It gets a little bit easier, but anyways, so that's not that difficult. So if they give you 3 of the velocities, it's really easy. It's one equation, solve for it, right? It's just some basic algebra. Now, in momentum problems, I always like to relate momentum to energy, okay? They are intertwined, and it's a good habit to get into. So whenever I calculate a momentum, I go back and I take a look at the initial energy and compare it to the final energy, okay? And these are all like little sums in front of everything. In this case, in this problem, the objects weren't falling. They were just moving across a flat surface, so there are no changes in potential energy on either side. So what we're going to have to do to figure out how much energy is lost is we're going to sum the initial kinetic energies, which is the initial energy, and compare it to the sum of the final kinetic energy, which is the final kinetic energy. All right? So let's go ahead and start off. The initial kinetic energy for the 2 kilogram block, we're going to put in its initial speed, which is positive 9 meters per second. That we're going to square. Now we're going to add to that the 1/2 10 kilograms and its initial velocity, which is negative 3 meters per second. We're going to have work. We're going to leave that in the equation. That's what we need to figure out. If there is work present, that means there is energy flowing in or out. So this question is asking, is work actually present? Which would be a difference. Is there a difference in the kinetic energies? Now what we're going to do is we're going to figure out the final kinetic energies. Okay. Well, after the impact, the block was moving at a negative 11 meters per second, which we're going to square. And the 10 kilogram block was moving at positive 1 meter per second that we're going to end up squaring. Okay. So this right here, this will cancel out, so you just have 9 squared. So this is going to be 81 joules. Right here, this is going to be 9 times 10 divided by 2, so that's 45 joules plus work. And this is going to be 2 divided by 2, so this is going to be 11 squared. And I think I know what 11 squared is. Times 11, 121. So 121 joules plus 1 squared times 10 divided by 2, which is just 5 joules. Okay, so 81 plus 45. Let's see what that is. 81 plus 45. 126. 126 joules plus 121 plus 5 is going to be 126. So the work done, well, work entering or leaving the system, or energy entering or leaving the system, is going to be the final energy. This is the final energy. This is the initial energy. And we are going to have to plot those up here. Okay, so this is going to be 126 joules minus the initial energy, which is 126 joules. So no work is entering or leaving the system. So work is equal to 0, so there is no energy lost or gained. So this should actually be stated is how much energy is lost or gained during the collision. All right. Well, we have a lot of stuff. Let's go ahead and let's reference some stuff. So the 10 kilogram block, I'm going to use red. The 2 kilogram block, I'm going to use blue. Okay, so I'm going to note those things right up here. So for the 10 kilogram block, well, let's establish coordinate system. So scale. So this is 12 meters per negative 12 meters per second down there. And this is positive 12 meters per second right here. And this is 0.01 seconds. Okay. And counting by twos. 2, 4, 6, 8, 10, 12. All right. So for the red guy, it starts off at negative 3 meters per second. So if that's 2, this is going to be negative 3. So negative 3 meters per second. And it ends up at positive 1 meter per second. So that is about right here. So this is positive 1 meter per second right there. So this 10 kilogram block, that is its change in velocity. So in other words, the acceleration, which is the slope of this line, is the change in velocity. So this velocity is changing. This is final velocity. It's going to be 1 minus negative 3. So this velocity is changing 4 meters per second across the 0.01 seconds. All right. I did that part just because I wanted to. I like detail. All right. For the blue guy, the 2 kilogram block, it starts off at, if this is 10, it starts off here. So this will be 10, this is 12. So this is positive 9. And it ends up at negative 11, which is going to be right about there. So that's negative 11, which is going to be right there. So this guy's velocity is drastically changing. Okay, and so the acceleration of the 2 kilogram block, that guy is dropping by, oh boy, what is that? That's negative 11 minus 9, so that's negative 20 meters per second that is dropping over the period of 0.01 seconds. Wow, that is a big change in velocity. All right. Over here, we are going to graph the energies, or the changes in the initial energy to the final energy. Okay. And these are the same numbers. So since you don't have to be too crazy, but let's just put positive 126 joules right here. And it's going to end here at 0.01 seconds. So its initial energy is right there. Its final energy is right there. So this has no change in energy. Okay. So the slope of that line, again, is power, which is the change in energy over the change in time, which is the work done over the change in time. So in this case, the work done is 0 over the change in time, which is 0.01 seconds. That's 0 joules. So the amount of power is 0 watts. Okay, so that's the amount of mechanical power being done. Okay, and so this is how I would like you to approach the tutorials. Okay, and what this does is this tutorial assignment, it's going to make you really good at understanding how momentum and energy work together, and how that relates to acceleration, and how that relates to power and the change in energy. So if you can do this tutorial, you will be about as good as I am at understanding momentum and energy. Okay? All right. Well, before we do more complicated problems, in elastic collisions, let me teach you something. So this is called the coefficient of restitution. Okay? So in this problem with the coefficient of restitution, what this coefficient of restitution is about, it basically is talking about how much, what I think of it as the energy dissipated or gained by a collision. Okay? In a way, it's not exactly equal to that, but that's how I interpret it. Okay? And they're saying the restitution, it's about the two objects when they collide, how well do they reform their original shapes, and how well do they absorb or rebound the actual energy, okay, during the collision. So I think of this as associated with work, as how much energy is being lost or added to the system. Okay, now if there is a perfectly elastic collision, like in this case right here, okay, so I'm going to kind of come over here and let's go ahead and calculate the coefficient of restitution. Okay, so how you do this is you take E and then you have the negative in front, and it doesn't matter the order at which you do this, just as long as you're consistent. So if you start writing the second object on the top for the difference in final velocities of the two objects, you start with object number 2. Make sure you start with object number 2 when you're doing the difference in velocity, in initial velocities between the two objects. Okay? So, for example, if you started with v2f minus v1f, on the bottom, start with what happened here? Start with v2i minus v1i. So in cases, you don't want to go v2f minus v1f divided by v1i minus v2i. You do it this way. It makes more sense this way too. And the fact that this negative is in front, that's talking about how the energy, it's looking about how energy is dissipated. So in reality, different coefficients of restitutions are between 0.85 and 0.95 for bouncy balls against bouncy surfaces. But steel, if you drop a steel ball, it is not going to bounce as high as a bouncy ball. And that's because the steel is going to absorb a lot of the impact, right? So let's see this in action right here. So, okay, so let's start with our V2, with our 2 kilogram object. So this is going to be V2, V final 2, and we're going to subtract from that the V final 10. And this guy is going to be VI2 minus VI10. So let's go ahead and plug in our values and see what number we get right here for E. Now, hopefully this is going to work out to be 0 because our work has to be equal to 0. Okay, so our final velocity of our 2 kilogram object is negative 11. And we're going to subtract from that the final velocity for the 10 kilogram object, which was positive 1 meters per second. Okay? Now, we are going to divide from that the initial velocity for the 2 kilogram object, which was positive 9 meters per second. And then we're going to subtract from that the initial velocity for the 10 kilogram object, which was negative 3 meters per second. Okay? So, keeping this moving, hopefully this E is going to be equal to 1. So now what we're going to get on top here is a negative 12 meters per second difference over 9 minus a negative 3, which is going to be a positive 12 meters per second. So this is going to be minus a negative 1. So that coefficient of restitution is equal to 1. So when there is no work, when the amount of energy flowing or leaving the system, when there is no change in energy, the initial energy is equal to the final energy, work is equal to 0, and we get a coefficient of restitution that is equal to 1. Okay? And so that is what we have with a perfectly elastic collision. So this is a perfect elastic collision. Now this equation is important because it's actually going to make what we're about to do a lot easier. Okay, so in the problem, if they state that it's a perfectly elastic collision, which in problems that we are going to do in our class, assume that they are a perfectly elastic collision unless you're told to not assume it. Okay, so in this case, if we have a perfectly elastic collision, this equation is going to become very valuable, especially in the case where we are given, let's suppose we're only given the 2 initial velocities, which is what we're going to do right now. Okay? So in this problem, it's the same exact problem that we just did, so we already know what the answer should be. Okay? But in this case, we are missing one of the velocities. So we have the 2 kilogram object, and we have the initial velocity of the 2 kilogram object, which is positive 9 meters per second. We have the 10 kilogram object's mass, and we have the initial velocity of the 10 kilogram object, which is negative 3 meters per second. But in this problem, we don't know the final velocities of both cars after the collision, so we need to calculate those. Okay, so we need to calculate the final velocity of the 2 kilogram car. We need to calculate the final velocity of the 10 kilogram car. And that is where this equation is going to become important. Okay, because since we have 2 unknowns, and if you were just using momentum, you couldn't solve it. You need a second equation. Well, I learned it using this energy way, which is horrible. The math starts to just get really cumbersome. But the math is a lot easier using this coefficient of restitution. And I'll show you what I'm talking about. So let's go ahead and do this using energy, and then I will do this again using the coefficient of restitution, and we'll see the difference in the two. Okay? So in fact, I'm going to move all of this up because I am actually going to need a large area to do the math. Okay, so let's go ahead and get started. So here we go. Let's start summing up the initial momentums. I'm going to use my little visualization trick, just like we had, 9 meters per second. And then we have the 10 kilogram object moving to the left at negative 3 meters per second. And that is going to be equal to 2 kilograms V final 2 plus 10 kilograms V final 10. So this is going to be positive 18 minus 30. So there's nothing crazy happening there. Then we get 2 kilograms V final 2 plus 10 kilograms V final 10. Okay. All right. And I'm going to just scooch this over. Okay. So that's our let's reduce this down a little bit. So this is going to be negative 12 kilogram meters per second equals 2 kilograms V final 2 plus 10 kilograms V final 10. Okay. Now over here with the energies, the very first lines aren't going to be too different. We're going to have to sum up the initial kinetic energies for both objects. Again, we're not going to assume work is present. We are going to assume work is present. So let's go ahead and let's calculate the initial kinetic energy for both objects together. So that's going to be positive 9 meters per second squared plus the initial kinetic energy for the 10 kilogram object, which is negative 3 meters per second that we're going to square. That's plus work, which is going to be equal to scooch this over. Let's try this again. Now I like to scooch the whole thing over. Thank you very much. This is going to be equal 1/2 2 kilograms V final 2 squared plus 10 plus 1 over 2 kilograms. Yep, 1/2 times 10 kilograms V final 10 squared. And so what we're going to get is, again, we're going to get 91 joules plus 45 joules plus work. And this is going to be 2 kilograms over 2. Just for the sake of making this problem not insane, in this part I'm going to write the units, but in the coming parts I'm going to leave the units behind, because when I show you this, it's going to get really busy. So this is going to be, I forget what was that, 126, I believe? Yeah, 126. So the initial energy is 126. Plus work. Well, in this problem, we are going to assume that this is a perfectly elastic collision. So I'm going to get rid of work. So, okay. So let's just do it this way. This coefficient of restitution, we're going to use 1 here. So if that's true, then work is equal to 0. Okay. So what I'm going to do is I'm going to show you how to use energy along with the momentum equation, to find both of those final velocities. And I'm going to show you how complicated it gets. All right. Now, over here we have this as our entry-level equations. And this is going to be 1 kilogram V final squared plus 5 kilograms V final 10 squared. So these are our two entry-level equations. So let's do this. Let's solve for V final 10 first. Since we have these two equations, what I've always learned is you got to take the less complicated equation and plug it into the more complicated equation. So if we're going to solve for V final 10 and get that as an n number, we have to remove V final 2. Okay, so what I'm going to do is, with the less complicated equation, I'm going to take this 10 kilograms and subtract it on to the other side. 10 kilograms V final 10 equals 2 kilograms V final 2. And then 12 kilograms meters per second minus 10 kilograms V final 10. We're going to divide this by the 2 kilograms for V final 2. And we're going to plug this in right here. Okay. So what we're going to get is 126 joules. Now I'm going to leave the units off. This will just be 1. And this, oops, what I should do is reduce this a little bit. So this will be negative 6 kilogram meters per second minus 5 kilogram V final 10, and that's V final 2. So I'm actually going to plug this in here. So what I'm saying is I'm going to take this guy and I'm going to plug it in there. Okay, so we're going to plug that guy in right here. I'm purposefully leaving the units off so the math looks easier and less busy. V final 10, and we are going to square this plus 5 V final 10 squared. So when we do this, we're going to have to FOIL this out. We're going to get 36 and minus, so negative 6 times negative 5 is 30 times negative 5 times negative 6. So that's going to be positive 60 V final 10, okay, plus 25 V final 10 plus 5 V final 10. And I forgot to put the little squares there. Let's subtract the negative 126 onto the other side. So this will be 36 minus 126 plus 60 V final 10. And we're going to add these two guys here. Actually, we'll do that in the next line. So 5 V final 10 squared plus 5 V final 10 squared. So these two we could add together, and we're just going to get, we'll get positive 30. So here is what we are doing. It's starting to look like a quadratic formula. So this is going to be negative 90. This is positive 60 V final 10. And this is plus 30 V final 10 squared. Now when we apply the quadratic equation, let me go ahead and do that, and I'll grab the solution real quick. Okay, so when I supplied the solution, what I did was I used C is equal to negative 90, B is equal to positive 60, and A is equal to negative 30. So when I did the negative B, so if I do negative B plus or minus the square root of B squared minus 4AC all over 2A, you get two different solutions. 1, where this is positive, you get this solution. So if we used this is the positive and this is the negative solution. Okay. Now if we look at this and we're solving for v final 10 right here, this v final 10, it's already, so it was moving to the left originally with negative 3 meters per second. So the negative solution is saying after it gets hit and pushed to the right, it has no change in its initial velocity. So this negative solution is not possible. This has to be the solution right there. So using this, what we have found out is that the final velocity of v final 10 is this solution right here. This is it. Okay. It may not always be the solution. You have to kind of logic your way through this. And again, how I did that, if this is 10 kilogram object, which we're solving for right here, if it's moving to the left at negative 3 meters per second and it gets hit by an object moving to the right, there's no way its velocity after that impact is going to be the same. It will have to change in some way. It may slow down. It may begin moving to the right. I don't know. But this is showing a solution where its velocity after the impact is a positive 1.0 meters per second. Okay. So now we could plug this back in for here. We could plug this one, this solution right here, and get v final 2. So v final 2, so this is final velocity of the 2 mass object. It's going to be negative 5 kilograms times 1, positive 1 meters per second, minus 6 kilogram meters per second. And so v final 2, negative 6, negative 5, actually, that shouldn't have a kilogram in it since we divided by a kilogram. Oops, sorry about that. Let's rewrite this again. This is just going to be a negative 5 here. Negative 5 times positive 1 meters per second. And this is negative 6 meters per second. So this is going to work out to be negative 11 meters per second, right? So we are able to find both of those using energy and assuming the work is equal to 0, right? Because the problem was described as a perfectly elastic collision. Okay. Now, the other way to do this using the coefficient of restitution is going to make the math a lot easier. So while I did this and this was really smooth looking, it isn't always very smooth looking. Okay. And with the coefficient of restitution, it only gives you one solution. It won't give you this negative solution. So it really does just gives you the answer, as long as you know the coefficient of restitution is equal to 1 or 0.85. But again, if it's a perfectly elastic collision, it's equal to 1. So let's see how this math is going to work out using the coefficient of restitution. So I'm going to do that. I'm going to move all of this stuff up, and I'm going to do that all again. But we're going to start off most of the way through the problem. So here's what I'm saying. Starting right here. Okay. So starting right here, we have negative 6 meters per second minus 5 meters per v final 10 equals v final 2. Now let's go ahead and write our coefficient of restitution. Okay, So that's going to be negative. And over here on this problem, we started with v final 2. So that's what we're going to start with over here. So this is equal to v final 2 minus v final 10 divided by the initial velocity of v final 2, which was positive 9 meters per second, and we're going to subtract from that the initial velocity for the v final 10. Okay? And we are going to assume this is equal to 1. So we're going to have 1 equals negative v final 2 minus, oops, I'm going to take this negative and leave it into the front. Be careful about how I write this. So this should be negative in the front. V final 2 minus V final 10 over 12. So now let's multiply both sides by 12. Negative V, I gotta do this again. So this negative is still here. V final 2 minus V final 10. Okay. And let's multiply this negative through. So that'll be negative V final 2 plus V final 10. Subtract the V final 10 onto the other side. V final 2. And then I'm going to multiply everything through by a negative. Right? And then we're going to get this really handy dandy solution. Where I multiplied everything by negative, and we'll get that. Okay, so now we just plug in this right here all the way up to the top here. And when we do that, we're going to get negative 6 meters per second minus 5 V final 10, and that's going to be equal to negative 12 meters per second plus V final 10. Okay? Now what we're going to do is switch a lot of stuff around. We're going to subtract that, we're going to add that 12 onto the other side, and we're going to add this onto both sides. So we're adding things to both sides. What we'll have is negative 6 meters per second plus 12 meters per second. And that's going to be equal to V final 10 plus 5 V final 10. This is going to work out to be 6 meters per second. And this is going to work out to be 6 V final 10. And that is going to just yield us that 6 divided by 6 is positive 1 meters per second as our solution. And plugging this into here, then what we would get we will get negative 12 meters per second plus 1 meters per second is equal to V final 2. And V final 2 is going to be equal to negative 11 meters per second. So of these two different ways of doing it, This one is a lot less complicated, right? Again, this energy solution is much more difficult. And then you have to apply the quadratic equation, which I did out of sight, which gave us two solutions. This one just gives you the one solution, and then it's much easier to work with. Okay? Okay. Let's go ahead and move on. Let's do an inelastic collision. So an inelastic collision, which I don't like the name of it, but it's a collision where the two objects collide and then they stick together. And then they kind of act as one object moving together. Okay? So even though they hit and stick together, again, we're going to have a situation where the object 1 is pushing on object 2 to the right, and then object 2 is pushing on object 1 to the left with an equal and opposite force. And since that time of that collision is the same for both objects, this impulse, again, the overall sum of the impulse is going to be equal to 0. Okay? If you wanted to figure out what the actual force was, you would just hit, you would compute this guy's initial momentum and compare it to his final momentum, and that will be equal to the overall, and if you knew the time of the collision, that would be the force of the collision. Okay? All right. Let's move on and let's do a problem where it is an inelastic collision. Now, just so you know, most, if not all, inelastic collisions, the kinetic energy is not conserved, or rather the energy is not conserved. That means there will be a difference in initial energy to final energy. Okay? Just like always, we are going to start these problems out with making a list of all of our variables, and then we're going to write that little picture at the bottom here. Okay? Okay, let's go ahead and make those lists. So we have a 2 kilogram block. It slides with an initial velocity to the right at 10 meters per second. And it collides inelastically with an identical block. Well, I think identical in shape box, but it's not identical. 4 kilograms. So mass of 4 kilograms. I think that meant in size. I don't know. Moving to the left at 5 meters per second. And so they're asking for what is the final velocity of both boxes. So we'll write those two velocities separately here, but what we're going to find out that they're actually, when they're combined together, they are just the same velocity. Okay, let's draw a pictorial representation. So here we have the 2 kilogram object. It's got an initial velocity that is positive 10 meters per second. Then we have an identical box, which identical in shape but not weight or mass. It's traveling to the left at negative 5 meters per second. Okay, and then after they hit, they are going to stick together. Okay, now when they stick together, it's like saying they have a combined mass of 4 kilograms plus 2 kilograms. And they are going to then be traveling to the left at some final velocity, which this final velocity is actually both of these final velocities. So these separate velocities they're just the same as this final velocity right here, which we are going to find. I love inelastic problems because they are so simple. Okay. Now, this momentum is going to be positive 20 kilogram meters per second. The 4 kilograms momentum is going to be negative 20 kilogram meters per second. And when they hit and combine, they are actually going to come to a stop. So the final velocity, you could see right here, in this particular case, which is 2 kilograms plus 4 kilograms, which I'm just going to write as 6 kilograms V final. So in this case, in this weird problem, the momentum comes to a stop. These two objects stick together. So what we find out is dividing 0 kilogram meters per second by 6 kilograms, the final velocity is 0. They don't always work out this way. In this particular case, it does. Okay? Let's see how much energy is lost or gained from this system. Okay? So here, that final velocity of 0, we are going to have to separate those two out, and I'll show what I mean here. So again, this is just two boxes sliding on the floor, so there are no potential energies. So we're going to have to sum the initial kinetic energies, and we are not assuming work is 0, right? It doesn't say perfectly inelastic collision. So here we go. The initial momentum or initial kinetic energy of the 2 kilogram box, this is going to be 10 meters per second, or we're going to square. We're going to add that to the initial kinetic energy of the 4 kilogram box that has a negative 5 meters per second squared, plus work. That's going to be equal to the 1/2 2 kilograms. Now, they both have a velocity of 0 in the end. So this is going to be 0 meters per second squared. And the 4 kilogram box is going to have a separate energy, which is also 0 meters per second squared. So this side is just equal to 0 joules. And so this is going to be 100 joules. This is going to be 5 squared, which is 25 times 4 divided by 2, so that's going to be 50 joules. And this is work. So the total initial energy is going to be 150 joules. So that is the total initial energy right there. Plus work. And the final energy is 0 joules. Right? I don't like that. That's a little too close. It looks like it's part of the equation. So I'll just say that is the final energy. Right? So when we subtract that 150 onto the other side, you have a total loss of energy of 150 joules. So even though there's a loss of energy of 150 joules, our momentum is still conserved because J doesn't exist. Okay? So let's go ahead and graph this. All right? So, okay, let's call this negative 12, and this is positive 12. the 4 kilogram object, I am going to use red. It starts off at, if this is 2, this is 4, so this will be -5 right there. It's going to end up starting at -5 meters per second. And it's going to wind up with a 0 velocity. So this acceleration of this object, of the 4 kilogram object, it's going to be rising up 5. So it's going to have a +5 meters per second over the period of 0.01 seconds. So that's a +5 meters per second change in velocity over 1/100th of a second. Okay. Anyways, now let's use the 2 kilogram object is blue. It starts off here at +10. And its velocity changes to 0 over 0.1 seconds. So this 2 kilogram object, and I should put 4 kilograms if I'm going to put kilograms here, its velocity drops by 10. So its change in velocity is -10 meters per second over the period of 0.01 seconds. That's its acceleration. Okay, now for the change in energy, the initial energy is +150 joules. So I'm just going to put that up here. So I'm going to make this +150. Okay, and it drops to 0, so its final energy is 0 over that 0.01 seconds. So the slope of this line, which is the change in energy over change in time, is going to be the work divided by time. So the power is going to be -150 joules loss over 0.01 seconds. So the amount of energy lost, which is going to be huge, I do know this, I just don't trust myself, so 150 divided by 0.01. So 15,000 joules. So that's the power loss. 15,000 watts of power loss. All right. Let's go ahead and, so this is a typical inelastic problem where two objects collide and they stick together. Now there's another type of inelastic collision problem where two objects start off together and then they explode and separate. So they start off together, moving or not moving, I don't know. And then they explode and head off in two different directions. Okay? So this is another type of inelastic collision. It's kind of like saying it's the opposite of this collision right here. Okay, let's go ahead and try this out. And this, I swear, is a problem from a textbook that I had a while ago. All right, so here we have Amy right here on the left-hand side. Now Amy, mass of Amy, she is 60 kilograms. And Gwen is on the right-hand side. She is 20 kilograms. And it says they are standing on slippery ice and they're going to begin pushing off against each other. So it looks like both of their initial velocities are 0. So they're at rest, not moving. Now, after they push, we need to figure out the final velocity of Amy and the final velocity of Gwen. Okay, so let's draw a picture of what we're working with right here. Okay, so you have Amy, who is 60 kilograms. Her initial velocity is 0. And then you have Gwen, who is 20 kilograms. Her initial velocity is also 0. Now, after they push off from each other, it says Amy is going to head to the left at 6 meters per second. So we know Amy's going to head to the left at 6 meters per second. So let's draw that right here. And Gwen is going to head off probably to the right. It's going to be to the right at some final velocity. So V final Gwen. And our job is to figure out what this is. Okay. Well, the initial sum of momentum is 0 kilogram meters per second. That's going to be equal to -6 times 60, so negative 360 kilogram meters per second. I just scooched it over a little bit. And that's so that should be negative 360 kilogram meters per second plus Gwen's mass times Gwen's final velocity. All right, we're going to add the 360 onto the other side. And divide both sides by 20. So 360 kilogram meters per second divided by 20 kilograms. V Gwen, so let's go ahead and put this into our calculator. 360 divided by 20, that is 18 meters per second, which is about 40 miles an hour. So I'm pretty sure poor Gwen is, well, she's definitely going to the hospital. But I didn't write this problem. Okay, so here we go. We have Gwen's final velocity. All right, let's see how much energy has changed here. It shouldn't say energy loss, it should say energy. What's the change in energy? Okay. Well, the initial kinetic energy, again, there is no change in potential energies in this problem, so we're going to sum the initial kinetic energy plus work, and we're going to set that equal to the final kinetic energy. Okay, so the initial kinetic energy in this case is just 0. So we're going to have work, which is going to just be equal to whatever this final kinetic energy is, which is going to be 1/2 Amy's kinetic energy, which is -6 meters per second, which we're going to square. And then we're going to add that to Gwen's kinetic energy, which is huge in comparison to Amy's. So let's go ahead and put some stuff in our calculator. So 6 squared, so that's just 36. 36 times 60 divided by 2. 1080. So 1080. All right. Let's figure out what Gwen's kinetic energy is. 18 times 18 times 20 divided by 2. 3240. So this is 3240 joules, which I could have left up on my calculator, but I'll just do it again. 3240 plus 1080. 4320. So work, the change in work, is going to be 4320 joules. So you're adding work to the system. So this explosion adds work to the system. Okay. There you go. Now, again, let's say this push lasts a fraction of a second, right? Let's go ahead and plot their velocities. So let's use Amy as red and Gwen as blue. Okay, so Amy starts off, if this is 18, so 1, 2, 3. So we'll start this going from negative 18 to positive 18. So every block is 3. So this will be negative 3, and this will be, every block is 3, so this will be negative 6. And then you got negative 12. This is positive 6, and this is positive 12. The period of time is 0.01 seconds. Okay, so let's graph this. So Amy's initial velocity is 0, so she's red, and then she ends up traveling to the left at negative 6 meters per second. So Amy's change in velocity is right there. Let's try that again. Okay, and so Amy's change in velocity is, so that's Amy. Her acceleration is going to be dropping by 6, so her change in velocity is 6 meters per second over 0.01 seconds. Gwen's change in velocity, she starts at 0, and she's heading to the right at positive 18 meters per second. So Gwen's Gwen's acceleration is positive 18 meters per second change in velocity over 0.01 seconds. Okay, so the initial energy is 0, but the final energy is 4320. So, and that's going to happen in 0.01 seconds. So we're just going to put this at 4320. All right, so this is just going to look like a huge number. So again, power, power, which is the change in energy over the change in time, which is equal to work over the change in time, which is equal to positive 4320 joules over the period of 0.01 seconds. So this power, the power is going to be a huge power. So 4320 divided by 0.01. 432,000 joules. 432,000 joules being added to the system. That is huge. That is enormous. Okay, we are almost done, and thank you for being patient going through these problems. Let's do one final problem, okay? Now, sometimes, so I know we have been using energy and momentum together, but we really didn't have to. So if we, for example, in this problem right here, we didn't have to use energy right here to find the final velocity. We could have just used momentum to find the final velocity. But there are some problems where it starts out like an energy problem and then leads into a momentum problem. Or it starts out with a momentum problem, then leads into an energy problem. Okay, so it's probably best if I just show you what I mean. Okay, so here we have a problem, and it looks like we have a bullet that is being fired horizontally, and it's moving initially at 10 meters per second, and it's going to hit a stationary block, which is this picture right here. Now, in this middle part, after they hit, they're going to combine in an inelastic collision. Now they're going to be moving to the right, where eventually they're going to be struck by a spring, which is going to bring them to a stop. That's what it's saying. And the spring constant is 5 newtons per meter, and we want to know how far that spring compresses. Well, how you do these problems is think about where the impact happened. Did it happen at the beginning of the problem or at the end of the problem? And so, and when I mean impact, I mean collision. So when did the two objects collide? Well, they collide right here, from initial to middle. So this problem is going to start out with a momentum collision problem. And then, since we have a spring in the end, we are going to use kinetic energy to figure that out. So here is what I'm saying in this problem. Let's start out with our collisions. So the initial momentum, we have a bullet, which is 1 kilogram. I'm just going to go for it. That bullet is traveling to the right at positive 10 meters per second. It's going to strike a box that is not moving. After they hit, they are going to combine into one object, which is going to be 1 kilogram plus 4 kilograms, moving at some final velocity. Okay? All right. So let's figure out what that velocity is after the impact. Let's do that real quick. So this is just going to be positive 10 kilogram meters per second. This is 0, so I'm not even going to note it. This is going to be a combined mass of 5 kilograms V final. So, solving for V final, we're going to have positive 10 kilogram meters per second divided by 5 kilograms. And so that's going to result in a positive 2 meters per second after the collision. So this is their velocity after the collision, and I probably should have used V sub m, because that's what the problem says in the picture there. So we'll put a little m. So this is like the middle energy. So now we know how fast the block and the bullet are moving to the right before it strikes the spring. Now, this is an energy problem. Okay, so let's go ahead and do this. We don't need, by the way, in inelastic collisions, you don't need to use the coefficient of, well, this coefficient problem, the coefficient of restitution problem. Okay? Okay, now, looking at this picture, is the block and the bullet moving? Yes. Do they have a height greater than 0? No. Are they touching a spring? Not yet. Okay. In the end, in this final picture, are they moving? No. Do they have a height greater than 0? No. Are they touching a spring that is compressed or stretched? Yes. So here is our initial energy plus work. That's going to be equal to our final energy. Now, in this problem, there was, if we do a little force diagram, there was no outside forces or energies coming into play. So really, in the end, so the only force touching it when it was fully combined, and I'll draw a little force diagram right here. It has the normal force up, and this is the block and the bullet, it has the mg force down. And what is bringing it to the rest? What is slowing it down is k times x. Okay? I'll give you space for on your problem to do a little force diagram to double check to see if work is present. Okay? So looking at this force diagram, since there is no friction, it's on a frictionless surface, the only force that is, since it's moving to the right, it's got a positive velocity in the x direction. And during this period of time, the acceleration will be to the left, so that's going to have a negative acceleration there. Well, the only force that is parallel to the displacement, which is the velocity vector in the x direction, is this k times x vector. And so if that's true, then there can't be any work in this problem. If there was friction present, then yes, we would have to include work due to friction. Or if there was a person's hand pushing it to the left, we'd have to include that push. But there are no outside forces, as shown by this force diagram. Okay, well, what we have in this problem is here's the kinetic energy right here of this object. So the kinetic energy of the object is going to be 1/2, and it's going to be the mass, which is the 1 kilogram mass plus the 4 kilogram mass. You have to be careful because this is 5 kilograms, right? Traveling at this velocity. So this is the initial kinetic energy of the bullet block object before it hits the spring. After it hits the spring constant k, so this is k times x, and let me write that so it doesn't look like it's part of the equation. So that is k times x actually, nope, I'm so sorry. It's 1/2 kx squared. And again, this is just 1/2 mv squared. Well, that's going to be 1/2 times k, which we said k was 5 newtons per meter, and x squared, which is how far the spring gets compressed from its equilibrium position. Okay? So what we're going to have here is we're going to have a 1/2 times 5 kilograms times 4 meters squared per second squared. And that's going to be equal to 1/2 times 5 newtons per meter x squared. So what we're going to end up with is, what is this going to be? This is going to be 20, this is going to be 10 joules. And let me just make sure, so that's 20 divided by 2, so that's 10 joules. And that's going to be 5 newton meters. So this is going to be 2.5 newton meters x squared. So 10 joules divided by 2.5 newton meters is going to be x squared. So that is going to be equal to 10 divided by 2.5 equals 4. So that is going to be 4 meters squared. So square root 4 meters squared, and that is x. And so x is going to be equal to 2 meters. That is how far the spring gets compressed. Okay, and so this is what you're supposed to do. I'm going to get rid of these. I don't know why they're there. This is what you're supposed to do when you have a problem where it has an energy problem, or it starts out with an energy problem like a spring pushing it, and then they separate later on, right? The reverse of this. So you got to ask yourself, where does the collision occur? Does it occur at the beginning of the problem or at the end of the problem? And so if it occurs at the beginning of the problem, start off with momentum and then work your way over to energy. If it starts off with energy, then you have the energy problem, then work your way over to momentum. Okay? All right. I hope you guys enjoyed 6.1. I know it was long, but I wanted to show you a lot of things. Thank you very much. Bye.